Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor, Department of Mechanical Engineering of JIS College of Engineering, Kolkata. Today's session we will discuss about how to find the atomic packing factor of FCC and HCP crystals and how to calculate the density of the density calculation, that is volume density. So we are discussing in module number 1, that is crystal structure, and today's subtopic is APF of FCC HCP crystals. Learning outcome: after going through this session, we will understand that atomic packing factor, how to calculate atomic packing factor of FCC and HCP crystals. So as we know, the atomic packing factor definitions, that is the fractional amount of volume or space occupied by atom in an unit cell is called atomic packing factor, APF, or atomic packing density or efficiency. So APF is given by an equation, that is volume of an atom, volume of atoms in unit cell by volume of atoms of the total unit cell. So atomic packing factor, in the last session we have discussed about for the simple cubic structure and body centered cubic structure. So today we are going to discuss, that is first of all, face centered cubic structure or FCC structure. So as we can see, the FCC structure atom or unit cell, there are 8 corner atoms are there and total 6 faces are there. So the 6 face contains atoms. Now the face atoms are touched by the corner atoms as shown in this figure. So if we consider the faces of A, B, C, D, so we can see is very clearly that in face there is total whole atom present, that is radius of 2r, and the corner atoms, that is R and R, that touches the face atom. So total, that is, we can calculate that B to D length, that will give us 4r. Now we know that for a cubical structure, the lattice parameter A is constant in any direction. So A lattice parameter of FCC structure and R is the atomic radius. Now from this figure it is clear that the dB square is equal to DC square plus CB square. So 4R square is equal to 2A square. Therefore the relationship between the lattice parameter and atomic radius for an FCC structure is given R is equal to A by 2 root 2. Now APF, from the definition we know average number of atoms per unit cell into volume of an atom divided by volume of the unit cell. So from the earlier discussion in the last session, we have came to know that average number of atom per unit cell in a FCC structure, that is effectively equal to 4, and volume of an atom taken as an Hertz sphere, that is 4/3 pi r. So here r value we are replacing by A by 2 root 2. So that is the total APF calculated in whole fractional number, that is 0.74. It indicates that in an FCC structure, 74% of its unit cells are occupied by the atom and remaining 26% are vacant. So some of the common material at room temperature found FCC structure, their lattice constant and atomic radiuses are given. So for a metal copper that is found FCC structure at room temperature, lattice constant A is given 0.3615 nanometer, atomic radius 0.128 nanometer. For gold, the lattice constant A 0.408 and atomic radius 0.144 respectively. Lead 0.495 and 0.175, that is lattice constant and atomic radius respectively, measured in nanometer. For nickel, lattice constant E 0.352 and atomic radius is given 0.125 nanometer. Silver, that is 0.409 and 0.145 nanometer respectively, that is lattice constant A and atomic radius R. For aluminum, that is 0.405, that is lattice constant A, and atomic radius, that is 0.14, that is atomic radius, measured in nanometer respectively. Now next is, that is hexagonal closed pack structure. Hexagonal closed pack structure, as we can see here, total number of, that is atoms present, as we know, that is equal to, in an hexagonal closed pack structure, that is equal to 6. Here in hexagonal closed pack structure, the faces, top faces and bottom faces are in hexagon. So in hexagonal structure, as we can see, the corner atoms, 6 corner atoms are there, and 1 face atoms are there in hexagonal faces. So there are 2 faces at top and bottom. So there are total 6 and 6, that is total 12 corner atom, and 2 face atoms are there. With addition to this, as we can see, that is 3 interior atoms are present in hexagonal closed pack structure. So as we can see from the figure, that volume of the unit cell here for an hexagonal closed pack structure is found out by area of the basal plane and multiplying its height by the total height of the unit cell. So here, as you can see, that height of the unit cell is taken as C, and the for an basal plane, as you can see, it is an hexagon, that is A, B, C, D, E, F, G, as shown in figure, point number B, figure B. So one hexagonal hexagonal length, unit length, that is equal to taken as A. So as we consider, that is for an hexagon, we consider at a small part or small area of that hexagon, that is one part, 1/6 of its part. So that is given by ABC, that is height, here it is taken as H. The corresponding angles are given, that is 60 degree each, and A to B, that is length of one hexagonal axis, that is A, small a, and AC length also small a. Now we need to find area of the triangle ABC to find out the total area of the hexagonal bases. So it is given by simple formula half into base into height, as we can see, and height in terms of here, that is sine 60 degree. So that will give us, that is half into a square sine 60 degree. Therefore, total area of AB DEFG, that is 6 into this small of triangle of ABC, that is ultimately we find out that is 3a square sine 60. So volume of unit cell, now area of base into its height, that is 3a square sine 60 into C. Now from this HCP crystal structure, the corner atoms are touched to the center atoms on top as well as the bottom faces. That is, the atoms at A, B, D, E, F, G are touching the C atom, that is interior atom or center atom. So here in this case, A, that is lattice parameter, that is a small hexagonal lane, A will be 2R, that is R is equal to A by. Now we need to calculate the APF, which is again from the definition, that is average number of atom per unit cell into volume of an atom divided by volume of the total unit cell. So from the earlier discussion, we know that average number of atoms per unit cell, it is calculated as 6 for the HCP structure. And volume of an atom, that is 4/3 pi r cube, considering the volume of the atom is an hard sphere, and total volume of the unit cell. So we have calculated just now, that is 3a square sine 60 into C. So ultimate the equation became, that is pi into A by 3c sine 60. So the unknown number from the earlier equation, as you can see, that is C by A ratio we need to find for the HCP crystal structure. And for uniform packing of this structure, which is tightly closed packed together, the C by A ratio for HCP structure is 1.633 nearly. So how to find or how to calculate this C by A ratio for an ideal hexagonal closed packed structure? That value is 1.633. So as we can see, there are 3 interior atoms at plane B, we can see, and the corner atoms that presents at plane A at top plane and bottom planes, which is denoted as plane A, as you can see. Now we need to understand this geometry, that 3 interior atoms are touched with each other, such as their centers are Q, R and S respectively. And these interior atoms are touched by again the above and bottom planes atom, that is center atom, that is taken as. So now we need to draw the perpendiculars from the top and bottom center of the atom. So here it is taken only the top center atom, that is from P, perpendicular drop to the plane of interior atom center, joining center, that is QRS. So from that QRS plane, from P, it is perpendicular drop to the plane which is cut at point T. Again, from the R of the center atom, interior atom, that a perpendicular is drawn on the QS plane that is cutted at U, and from that above P point, if we draw a perpendicular that is up to T in the QRS plane, so it cuts at RU at T. Now we are joining T and S. So the atomic arrangement of plane A and B is shown. PQRS, the center of atom of plane B, and point P is the center of atom just below and above this three atoms at plane A. Now QR equal to RS is equal to SQ, as you know, is equal to A, and C is twice the normal from the point P on plane QRS, as because C is the total height. So C is the twice the normal from the point of P, considering for an ideal structure. So C by A is equal to twice the length of C, that is 2pt, that is the length of pt distance from the any one of the above or bottom center atom to the plane of interior atom's plane, that is QRS. And A value, as we know, that is equal to RS. Now from the geometry, we know that RU is calculated root over RS square minus SU square, that is equal to A square root over of A square minus SU is equal to, that is E by 2, that is A square by 4. So ultimately RU value we can find out root 3 by 2 into A. Now from the geometry, as we see earlier, that is RT is equal to 2/3 of RU. So the RT value now becomes A by root 3. Now PT value, that is equal to given root over of PR square minus RT square. So that is given by ultimately, as we know, PR is equal to A, and RT value we have just find out, that is A by root 3. So ultimately PT value is root 2 into A by root 3. Now the C by A we can put it directly, that is 2pt by RS. So PT value we have just calculated, that root 2 by root 3 into A. So 2 into root 2 by root 3 into A, and A value, that is given as RS, that is which is equal to A. Now if we calculate this one, which will give, that is 1.633 approximately, or nearly 1.633. So for an ideal hexagonal closed packed structure, the C by A ratio will be 1.633. Now we are putting the C by A value 1.633, and sin 60 we value, if we calculate numerically, that is 0.866. So we will get APF equal to 0.74. So as we can see, for FCC structure and HCP structure, the atomic packing factor or atomic packing density or efficiency is 74%. That means 74% of this unit cell occupancy is done by the atom and remaining 26% are remain vacant. So some of the metals having HCP structure at room temperature with their lattice parameters and atomic radiuses are given in the table. So metals cadmium, zinc, titanium and etc. materials are found HCP structure. For cadmium, lattice constant A and C is respectively given 0.2973 and 0.5618 nanometer respectively. The atomic radius R is given 0.149 nanometer. The C by A ratio for an cadmium, that is measured at room temperature, that is 1.890, which is from an ideal hexagonal close-packed structure. The deviation is plus 15.7%. For an zinc, the lattice constants are given A and C respectively, that is 0.2665 and 0.4947 nanometer. Atomic radiuses, that is 0.133 nanometer respectively. The C by A ratio again deviates from 13.6% from the ideal hexagonal close-packed structure, and the C by A ratio, that is 1.856, which is 13.6% deviation from the ideal hexagonal close-packed structure. Now next is titanium. The lattice constant A and C correspondingly given 0.2950 and 0.4683 respectively. The atomic radiuses, that is 0.147 nanometer respectively. C by A ratio, that is given 1.587. Now in this case, the C by A ratio deviates in negative for an titanium, that is minus 2.81%. So apart from this, that is beryllium, zirconium, cobalt, magnesium, etc. element or metal found hexagonal close-packed structure at the room temperature. Now next part is, that is density calculations or the volume density. The volume density of a metal can be calculated as, that is weight of the atom in the unit cell divided by volume of the unit cell. So now weight of the atom in the unit cell is given, that is average number of atoms in the unit cell multiply into atomic weight, and volume of the unit cell, that is Avogadro number n multiply into volume of the unit cell. So ultimately that is given summation of A divided by n into V, where summation of A is taken, that is sum of atomic weight of atoms in an unit cell, Avogadro number, that is 6.02 into 10 to the power 23, and volume V is the volume of the unit cell. So now we need to calculate the density of an BCC iron. So the question is, that is determine the density of BCC iron which has lattice parameter given 0.2866 nanometer. Solution, that is atoms per cell, as we can calculate from the earlier discussion. We know for a BCC structure that is equal to 2. and atomic radiuses are given, that is 0.2866 nanometer, which is equal to 2.866 into 10 to the power minus 8 centimeter. The atomic masses are, that is given by, that is 55.847 gram per mole. So volume of the unit cell, that is equal to A cube, A0 cube here. So that will give us total volume, that is 23.54 into 10 to the power minus 24 centimeter cube per cell. Here now Avogadro number n, which is equal to constant, that is 6.023 into 10 to the power 23 atoms per mole. Now the density rho, which is given number of atoms per cell into atomic mass of iron divided by volume of unit cell into Avogadro number. So atomic number of atoms per unit cell for an BCC structure or BCC iron. BCC iron shows BCC structure in room temperature, that is equal to 2. From the earlier discussion we know. Atomic masses, that is given, that is 55.847 gram per mole. So we need to, the Avogadro number, we need to divide it, that one, that is, we calculated that volume of the unit cell 23.54 into 10 to the power minus 24 centimeter cube per cell, and Avogadro number is 6.02 into 10 to the power 23. So thus we calculate the density of BCC iron, which is shown as room temperature, that is 7.822 gram per centimeter cube. So with this, we are likely to conclude this session. These are the references given. Thank you for joining this session.